We will be looking at question 17, October 2021. In this question, it's about transition elements, and we've got some calculations as well. Now, this is the third paper so far that we're doing. We did 2023, we did 2022, this is 2021. And you know what, even as little as 3 past papers, you're seeing repeated questions even. Let's have a look. It says, in this question, it says most D block elements are also classified as transition elements. Explain why scandium and zinc are classified as D block elements, but not as transition elements. Your explanations must include full electron configuration. What does it mean by full? They don't want you to use noble gas shorthand electron configuration. E.g., if you've got, say, magnesium electron configuration, which is atomic number 12, you can't write that down as Ne and then 4s2. Yeah, you can't, not 4s2, 3s2. They don't want the shorthand. So let's cross that out. Now, so explain why scandium and zinc are, why they're not transition elements. First of all, what is a transition element? A transition element, this is a definition, this has come up recently as well. A transition element which has an incomplete D subshell. That's the definition. Not all D block elements are transition elements. Let's, using this definition, have a look at why. You see, with scandium, scandium has an electron configuration. Scandium has atomic number of 21. And what's the other one? Zinc has an electron configuration of 30. Let's look at the electron configurations first. 1s2, 2s2. By the way, how do we do electron configurations? It's a bit of a year 1 recap. You've got your subshells. Actually, I don't like the way I've written that. Let's try again. These are your electron shells, first electron shells, second, third, fourth. The first electron shell only has 1 subshell, the S subshell. The second electron shell has an S, the S, P, and a D. The fourth electron shell can be split into 4 subshells. And you see the order in filling is follow the direction of this arrow. 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then 4p. You're required to write the electron configurations up to and including for the element krypton. Anyway, back to our question here. So you've got zinc, so scandium, 1s2, 2s2, 2p6, 3s2, 3p6. And then after 3p6, you fill in the 4s subshell, 4s2, and then you go back to the 3D subshell. In this instance, the subshell only has one electron. This is for the element. Now for zinc, it's going to be the same format. Then 4s2, and then 3d10. Notice I fill in 4s subshell before because it's at a lower energy level, and then the 3D subshell after. But I write it in numerical order. Now, what is meant, so this is the definition of a transition element. What is meant by a D block element? The fact that its D subshell has the highest energy. So you can write that down. The fact that the D subshell is at the highest energy or energy level. You see, which, if it was a group 1 element, the highest energy level is in the S subshell, could be 3s, 4s, 5s. So this is the definition of a D block element. Now, if you look at the ions of zinc and scandium, scandium only has one ion. That one ion is Sc3+ only. And zinc only has a 2+ ion. And if you look at these, if you look at the subshells, the electron configuration, scandium, it actually loses the 4s subshell, and in the 3D subshell, there's 0 electrons. Zinc, the 4s was taken off. The 4s is lost, and the 3D subshell has 10 electrons. The subshell. You see, look at the word used in the definition: incomplete or partially filled. Not fully, partially filled. Oops, not filled. Partially filled. You see, the 3D subshell is empty. And in zinc, the D subshell is completely full. Neither of these two are partial. Let me just highlight those. Empty and completely full. That's why scandium and zinc are not transition elements. Moving on. You see here, you've got information about compound A. It's a hydrated chromium salt and you've got your molar mass over here. You've got the empirical formula, sorry, not empirical formula, you've got the percentage abundances, which we can in turn work out the empirical formula. The student dissolves compound A in water. The resulting solution contains the complex. So you know the chromium has a 3+ charge. The student mixes the solution with aqueous sodium ethane dioate. Ethane dioate. A ligand substitution takes place, forming a solution containing 3 stereoisomers of complex ion of chromium 3. Complex ion B is a 6-coordinate complex. It contains 2 of the ethane dioate ligands and 2 water ligands. Now it says here, what is meant by a bidentate ligand? Before I even answer this, you see in the previous year paper, sorry, this is 2021, so the year after, they asked a question, the examiners asked, why does, let me write this down, why does ethane, whoops, why does ethane 1,2 diamine act as a bidentate ligand? This was asked the year after. This is a 21 paper. And the answer to that question and the answer to this question is the same. What is meant by a bidentate ligand? First of all, what is meant by the term ligand? It's a molecule or ion that donates a pair of electrons to form a coordinate bond. In this case, you've got the term two. Two, meaning bi, dentate is like sort of a dental word, like teeth. And the ligand is what it means by the fact that it donates a pair of electrons to form a coordinate bond. But because you got bi, it refers to two. So in what it was meant by this, the fact that it donates two electron pairs to form two coordinate bonds. It's an identical answer to the 2022 paper, but the question is worded differently. As it's said many, many times, there are many, many, many questions, but the answers always tend to be the same. They always emphasize those same points again and again. Question after is asking, determine the formula of A and B. What is A? A is compound A is the hydrated salt. Compound A. And then you've got the complex B. Identify them. Write an ionic equation for the ligand substitution and show the 3D structures for the 3 stereoisomers. Let's have a look. Now, first thing first, you've got your percentage abundances, and let's work out the empirical formula. So the elements we have, let's capture this data. We've got chromium, 17.10, hydrogen, oxygen, and sulfur. Hydrogen is 3.94, oxygen is 63.13, and sulfur is 15.83. These are percentages by mass. Because these are percentages by mass, we can refer to them, we can divide them by their relative atomic mass to determine the molar ratio. Oops, what did I just do? 15.83. Chromium, 52. 1, 16. Sulfur is 32.1. Let's work these out on the calculator. Now, the next step, once you work out the sort of molar ratio or relative molar amounts, mole relative amounts in moles, sorry, you divide all of them by the smallest number. So this gives you, the smallest number in this case is going to be this. So that divided by itself would be it's going to be 3.94 divided by 0.329. That gives us 11.975. That's going to be 12. This will also then be 12. And the last one okay, this is 1.498, and rounding it up or down is too much, so we can put that as 1.5 because you can't round, that's too much rounding. Now, because it's too much rounding, we need to work with whole numbers, so we just double everything up. So that will become 2, 24, 24, and 3. So the empirical formula will therefore be CR2 H24 O24, and you've got S3. Now, looking at this, we know that it's a hydrated compound, so we're going to extract as many waters as we can from this. And if we do that, what's the maximum number of water molecules we can extract? It will be, let's use the hydrogen. That would be 12 H2O. Let's write that down here, 12 H2O. That will leave us with a leftover S3 and O12. Now, if we divide that by 3, that actually gives you an SO4. So we're dealing with a sulfate. So that's going to give us CR2 chromium sulfate. Remember, there's 3 lots of that. Dot, because it's a hydrated compound, 12 H2O. 12 H2O. Yep. Now, we've established the formula of compound A. Let's look at what's this? Has a molar mass of 608. There didn't seem to be any reason to use this number except to verify if we've got the right answer. Yeah, it doesn't seem to be any reason to need that. 608.3. We don't need to do this, but I'm going to just do this. Let's see if this adds up to 608.3. Have a little look. 52 plus 52 plus 3 sulfurs, 12 oxygens, and 12 waters. Yep, 608.3. That seems to verify that, but we don't need to include that in our answer. Let's look at determine the formula of B. Now in B, it tells you that there's 2 ethane dioate ligands and 2 water ligands. So they also want the formula for the ligand substitution. Now, you've got your complex, which is Cr, which is surrounded by 6 water molecules with a 3+ charge. And you've got your ethane dioate ligands, C2, 2 carbons. There's going to be 4 oxygens and it has a 2- charge. So this is your ligand. This goes on to give you the complex. There's still 2 water molecules left per chromium ion, and now there's going to be 2 lots of ethane dioate ions. Ugh. And 2 of those. And in terms of the charge, you've got +3 here. You've got 0 from the water, and you've got a 2- and another 2-. That the total charge therefore adds up to -1, or just minus. And you've got the 4 water molecules that are going to be given off. And to balance, you put a 2 there. You have your ionic equation for ligand substitution. Because you are swapping the water molecules for the ethane dioate ions. So we've got compound A. Compound B, we've got the structure of compound B, which is this. Sorry, complex B. And it wants us to show the 3D structures for the 3 isomers. You've got 3 of them. Before we even start this, what we can do is draw the framework for the 3 complexes. It's a nice drawing exercise. Again, if you look at the past questions we've been doing, this type of question has come up before, where you got 2 bidentate ligands and 2 monodentate ligands. You got your ethane dioate ions. So let's draw. There's going to be the trans version, there's going to be the cis version, and there's going to be the optical isomer of the cis stereoisomer. You'll see from the previous question, the previous year we did, you've got that there. Ethane dioate ion looks like this. This is a trans version. So you've got the water molecules on opposite ends. And so your bidentate ligands will be like this. What's the overall charge? The overall charge is a -1. Don't forget that. Let's draw the other one. Let's draw the cis version. Cis means together. So the cis is going to be got your water molecules. Remember, the connection has to be with the oxygen. It's the oxygen that's forming, donating the pair of electrons to form a coordinate bond. Be mindful of that. You lose marks if the connections are not there. That's the cis version, and we will draw the optical isomer of this, meaning the mirror image. So we're drawing the mirror image. Let's put the mirror there. Show mirror. Oops. Look how we draw it. Oops. Yep, I'm back. Got your ethane di-O8 ions. Got a minus there. And I believe we've covered everything. So let's have a look through the mark scheme. Ethane di-O8 looks like, where's the double bonds? Why haven't I drawn the double bonds? Apologies. Di-O8. Yep, I'm sure you can draw it a bit neater than mine. I tried to squeeze it in a small space. But otherwise, let's look at the points. You've got chromium, you've got the example of the working. We've got that there. Remember to times by 2, because you got the 1.5, we want to make that into a whole number. So 1.33, to make that a whole number, you need to times it by 3. I've seen examples like that as well. You've got your hydrated dot formula, you've got your ligand substitution, you've got your structures, and that pretty much covers all the indicative points. Just making sure I've got all that's being covered. Yep, that's it, ladies and gentlemen. The rule is, when you've got two, just to emphasize the last point, and I'm going to finish here, when you've got 2 bidentate ligands and 2 monodentate ligands, it gives rise to 3 different isomers, 2 of which are stereoisomers, and the third one is an optical isomer of the cis version. Again, I believe in the 2022 or 2023 paper, this type of question came up, but in that example, we were dealing with chloride ions. And we was using ethane 1,4,1,2-diamine as the bidentate ligands. As we said before, the questions are many, but the answers tend to be the same. That makes the end of this question. And before I sign off, I'd just like to say, we've done about 18 videos so far. If you've made it this far and are watching these on a mostly daily basis, I want to congratulate you that you are fighting against being average, you are fighting against being mediocre, you are pursuing excellence, and I want to commend you for that, and I want you to continue with that. Persevere in giving yourself a dose of inorganic questions daily. I will see you tomorrow.